today we are continuing graphing rational functions. I have 3 more examples prepared for you. They all look very, very different. They're here on the left-hand side, and they're on the bottom of that note, graphs of rational functions. So remember, we have 6 steps to go through. Number 5 is usually not needed, but there are at least 5 things we need to do in order to graph these. So I'm going to go over to the what I have set up here. I have a graph set up here, and we're going to do all of the calculations below. So I recommend that you just do this all on a sheet of graph paper. Okay, so our first function is going to be f at x equals x squared minus 1 over x plus 1. Sorry, x minus 1. Okay, so the first thing you want to do is factor the top or the bottom if possible. Notice that this is a difference of squares. So we can factor this to x plus 1, x minus 1, divided by x minus 1. Notice that there is a common factor of x minus 1. So this whole function can be reduced to just x plus 1. So this function is actually just a line, x plus 1, with a hole at 1. Okay, there's a hole because you have a discontinuity here, because the original question has a denominator and the denominator can't equal 0. So even though it simplifies to x plus 1, we still have to consider this denominator, and that will create a hole. So there's no vertical asymptote because our final line doesn't have any denominator. So this is a hole at x equals 1. Okay, to find the y value, you just put 1 into the rearranged function, and you get 2. So therefore, the hole is at 1, 2. Okay, there are no other discontinuities. There's no horizontal asymptotes, because really once you rearrange it, it's not even rational anymore. Okay, so then the next step is to write the domain. So it is x such that x cannot equal 1. But it's in the set of all real numbers. Now we need to find the y and x intercepts. So f at 0 is just 0 plus 1, so 1. So 0, 1 is the y-intercept. And then to find the x-intercept, we set the numerator equal to 0. Excuse me. So x plus 1 equals 0, so x equals negative 1. So negative 1, 0 is the x-intercept. All right, so this is just a line. We actually don't need to do any more of the calculations because we know that x plus 1 is just a line, but there's a hole at 1, 2. So we can sketch the hole at 1, 2. You just literally draw a hole. Our x-intercept is at negative 1, 0. Our y-intercept is at 0, 1. And you can just draw a straight line through those points. Okay, actually here, but you can't draw a line there. So then on here, I'll stop my line there and draw a new line after that. And there you go. And that is your function. And you can label these points. So this hole is at 1, 2. The x and y-intercept is 0, 1, and the x-intercept is minus 1, 0, and this is your function f at x. Okay, so just a reminder, for any questions where there's a common factor and you can cross it off, that just means that there's a hole created. So the graph will look like, the graph will be whatever results after what you cross off is gone. So if after what you cross off is gone, you just deal with graphing that, and then whatever you crossed off will create a hole. So it will look like, the picture will look like whatever is here, the simplified version, with a hole at whatever is crossed off. So let's say, for example, you have like x plus 3, x minus 1, x plus 5, divided by x minus 1, x plus 2. Okay, so this would simplify to x plus 3, x plus 5 divided by x plus 2. So there would be a hole at 1, okay, at 1, and then you'd put 1 into this function to find out what the y value would be. There would be a vertical asymptote at -2, and there would be an oblique asymptote that you would have to find because this is a quadratic on the top and a linear on the bottom, so that it's top heavy by exactly 1 degree. So this is the graph that you would be thinking about graphing, but you would just have to include a hole at x equals 1. Okay, let's go to our next function. Okay, the next one we're going to graph for you is f at x. F at x equals 2x squared minus 3 divided by x squared plus 1. Okay, so can anything be factored? That's what you want to ask yourself first. Well, there's no common factor at the top. It's not a difference of squares. There's no common factor on the bottom, not a difference of squares, so there's nothing I can do. Okay, so the first thing I'm going to look for is any vertical asymptotes or holes. So I set my denominator equal to 0, okay, and that gives me x squared equals -1. Now there's no solution to that. You can't square root a negative, so that means there's no VAs and there's no holes. So that's interesting because usually there is at least one of those. I do have a horizontal asymptote though. You'll notice that the top is a quadratic and the bottom is a quadratic. So therefore I have a horizontal asymptote at 2, since the ratio of the leading coefficients is 2 to 1, so it's just 2. I don't have an oblique asymptote, okay, because it's not top heavy. So now I need to go and find the y-intercept. So f at 0 is -3. So it's 0, -3. And now I need to find the x-intercept. So remember, for the x-intercept, you can just set the numerator equal to 0. So 2x squared minus 3 equals 0. So then that gives me x squared equals 3 over 2. So I actually have x-intercepts at plus or minus root 3 over 2. Okay, so it might be worth taking out a calculator and calculating to see exactly what that is. It's just above 1, okay? The square root of 1.5 would be just above 1, and it has it on either side, okay? Think about it, it would be smaller than 1 squared is 1, and 2 squared is 4, so it's pretty close to 1. Okay, now I need to find my positive, and no, I'm really confused with how this is going to look, because I have no vertical asymptotes, I have x-intercepts and a y-intercept. Let me just graph this stuff, because I'm starting to get a little bit confused about what this might look like. So I have a horizontal asymptote here at y equals 2. So let me draw that. Okay, and I'm going to label it y equals 2. All right. I have a y-intercept -3. Interesting. And I have these x-intercepts at negative root 3 over 2 and positive root 3 over 2. Okay, so it looks like it might be going down and then back up, but then what happens here? Okay, so let me check to make sure. I'm guessing that after root 3 over 2 that it's going to increase and then kind of approach this asymptote. And I'm guessing that before here it's going to be positive and increase this asymptote, and that in between here it'll go down and then back up. But I have to double check to make sure that that's true. So I have to check before my first 0 to see if the function is positive or negative there. Okay, so I'm just going to put an f at, like, I don't know, -3. Okay, so that would give me 2 times 9, right, 9, so 2 times 9 is 18, so that's 15 over 9 plus 1 is 10. So 15 over 10, so that's 3 over 2. So I have the point -3, 3 over 2, 1.5. So that's kind of confirming my suspicions there. So therefore the function is positive in this section. So everywhere from this 0 over, the function is positive. Okay, now I'm going to check between the two zeros, and I already know based on my y-intercept that it is negative, but I just need to show that. So f at 0 is negative 3, so therefore f at x is negative. Okay, and then after my 0, so x is greater than root 3 over 2, so I'm going to put in 3. I'm going to get the same thing as before. I'm going to get 15 over 10, so 3 over 2. So therefore, f at x is positive there as well. So after this 0, it's positive again. In fact, it looks quite symmetrical. So I'm going to guess that it's going down and then back up. So I also want to know if it actually ever crosses this asymptote and how it approaches it. There's nothing to say that this doesn't go over the horizontal asymptote and then approach it from the top. Okay, there's nothing that I've done to prove that it approaches it from the bottom. So I'm going to check if it ever actually crosses that asymptote. So I'm going to set the whole thing, this whole function, equal to 2 to see if it ever does. So I'm going to use a different color just so it's not confusing there. So 2x squared minus 3 over x squared plus 1. Does that ever equal 2? So then that I cross multiply, and you'll see that there'll be no solutions to this. Okay, because you can't have 2x squared minus 3 equaling something that's 2x squared plus 2. That just doesn't make sense. So therefore, it doesn't cross the horizontal asymptote. Okay, so from that, I'm pretty confident that this is going to go down and back up, and then through this point, and approach the asymptote like this. Okay, if you weren't sure of the shape, you can just throw in some more values. Sorry, that's supposed to be approaching. If you weren't sure, you could just throw in some more x values and see what it looks like. So let's go over to GeoGebra and see what this looks like. So that's the function, and you can see it looks pretty similar to what I just drew. Okay, it has a minimum there at -3 and an asymptote at y equals 2, and there we go. We did a pretty good job. Okay, I never did check on the first one, the straight line, but there we did it right. Okay, now we're going to do our very last example. Isn't this exciting? It's an interesting looking one. It's going to be quite complicated, so I'm going to get that analysis done for you. So at this point, if you're feeling a bit confused over any of the first two examples, you might want to take a break and just kind of like look it over and try to make sense of that information, because this last example is quite different than the other two. All right. So here we have f at x equals x divided by x squared plus 2x minus 15. So we can factor the denominator. What multiplies to -15 and adds to +2? It's x plus 5 and then x minus 3. Okay, that adds, I'm just going to double check. 5 times -3 is -15. 5 plus -3 is +2. Phew, I'm good. I notice that it's bottom heavy, so it's going to have a horizontal asymptote. And there's no common factors, so it won't have any holes. So my first step is to look for any of the discontinuities. So I'm going to have vertical asymptotes at x equals -5 and x equals, why is it doing that? X equals, let's do this again, vertical asymptotes at x equals -5 and x equals 3. Okay? No holes. And there'll be a horizontal asymptote at y equals 0. I know that because it's bottom heavy. Anytime something's bottom heavy, there's a horizontal asymptote of 0. Okay, so I can graph those up here with my handy dandy line. X equals -5, there's 1, 2, and x equals 2, was that the other one? I think. And then y equals 0. Okay, and then I can label all of those with the equations. Oh, it was supposed to be 3. Okay, so let me just erase this. Oh, I can't erase the line. Shoot. I'm just going to have to undo all this. There we go. Okay, sorry about that. Hopefully you guys caught that mistake before you drew your asymptote there. 3 and 0. Oops. And 0. Okay, so when you label everything, all right. Okay, so that's step 1. Now step 2 is to write our domain. So it's x such. Oh, you guys are laughing at me. Okay. X such that x cannot equal -5 or 3, and x is in the set of all real numbers. Sometimes my pen is worse than other times. I don't know what's going on. Okay, now we want to look for the intercept. So step 3 is looking for the intercepts. So the y-intercept, I just find f at 0. So when I put that in, I get 0. Okay? So 0, 0 is my y-intercept, which means, surprise, surprise, I'm going to have an x-intercept of 0, 0 as well. Okay, so let me go up and plot that point. Oh, I can't. Why not? Because there's an asymptote at 0. Okay, but actually, yes, I can. Okay, so that's what you might all of a sudden look at this and be like, oh no, I can't do it. Remember that horizontal asymptotes can be passed through. In this case, there is a point that makes the function 0, and that's when x equals 0. So that doesn't mean that it's not there. Remember that horizontal asymptotes just have to do with end behavior. So that means that as this function goes in this direction and then far in this direction, the function will be approaching y equals 0, but that doesn't mean that that necessarily is what happens in this middle section. Okay, so that's why I said this one's going to be a lot different. Okay, so now we have to figure out where this function is positive and where this function is negative. This is an extremely important step, and so that's why I'm putting it in red in a question like this. Remember, you have to consider all the zeros, so that in this case, that's x equals 0, and all the vertical asymptotes. So x equals -5 and 3. So this creates one section that's less than -5, one section that's between -5 and 0, one section that's between 0 and 3, and one section that's greater than 3. So this function has 4 sections. I'll show you how this looks. So the function will either be all above the x-axis or all below the x-axis in this section here before -5, before the first vertical asymptote. Then it might switch between -5 and 0. And then it might, again, if it's positive, it might go back up or it might go down. Or if it's negative, it might go back down and then up. We don't know. So we have to check on this side between 0 and 3. Is the whole function down here or up here? And then again, after this vertical asymptote. Okay, so there's 4 sections. So to do this, I literally just can plug in points. So I put in f at -6. And what do I get out of it? Well, I get -6 over 36 squared. 6 squared, which is 36. So I'm going to get a negative number. Okay, so you don't actually have to find the exact number. You can if you want that coordinate. But remember, you actually just need to know if it's positive or negative. So here, I'm going to put in, like, let's say -1. Okay, I'm just going to put in something easy. So I would get -1, right, divided by -1 squared. So 1 plus 2, which is 3, but then minus 15, which is -12. So I actually get 1 over 12, so it's positive. So f at x here is positive. Okay, between 0 and 3, what happens? Well, f at 1 would give me 1 over -12. So here it's actually negative. And then after 3, what happens? Let's put an f at 4. So I get 4 over some big number. So like 4 squared is 16 plus 2 times 4, which is 8. So 24 minus 15, so 9. So here f at x is positive. So I have negative, positive, negative, positive. Okay, so in this section, I'm guessing that the negative is going to be then something like this. Okay, if you want to see where this curve is, you could throw in values for -6, for -7, -5.5. It might make it look a bit better. Then I go from positive to negative. So what is going on here? This is a lot harder to do, and people often just put like a nice cubic through here. That's way too curvy. So in this section, I really do recommend throwing in values for x. Okay, so we found, what did we find here? -1 to be 1/12 and 1 to be -1/12. So -1 is just 1/12, like that's like super small. And 1 to be -1/12. So those look really, really close to the x-axis. So I wonder what -2 would be. If I put -2 into the function, I'm going to get -2 over 4. I'm going to get another really small fraction. So these actually stay really, really close. Okay, so I'm going to have you guys actually like work at putting in those yourself, but you'll see they get really, really small. So I think it's going to end up looking something like this, where it gets really close and then it goes down very quickly. And same thing here. And it goes up quickly. Okay, then it was positive, so it's safe to assume, okay, well, we found the point at 4, we get 4/9, which is almost a half, right? So it's going to look something like this, because it has to approach the asymptotes. Okay, so now you label all your points, and that's a pretty good estimation. Okay, again, you probably want to put in coordinates. To be honest, I don't have my calculator with me right now, but you should probably put in coordinates here to find out what everything is. And then you can check on GeoGebra to see if it looks right. So this is what h at x looks like. It's pretty similar to what we did. If I back out, okay, you'll notice that it is quite shallow here. Like this section goes pretty almost horizontal for a while and then just drops right off. Okay, same thing in here. If you wanted to do like h at -3, you can actually calculate points right on GeoGebra, so that's pretty cool. So that's only a quarter. H at -4 is 4/7. Okay, h at 3 won't work. H at like 2, okay, is -2/7. So you can actually use GeoGebra if you wanted to come up with these numbers if you're doing an assignment or something, just so you know. Okay, so that's a really funky looking rational function. Functions are funky. So that completes all 6 examples I'm going to give you of graphs of rational functions. You can see that they all have very different shapes and very different looks. There's all different kinds of discontinuities. Sometimes they pass through horizontal asymptotes, sometimes they don't. There's lots of different things that can happen. So it's up to you as the mathematician to do your analysis, do your due diligence, go through every step slowly and carefully, and use that critical thinking to inform you what this graph is going to look like. And remember, when in doubt, just use a table of values, okay? If you're really, really stuck, just start throwing in values for x and see what happens, what values you get for y, plot those, and, start connecting the dots if need be. So guys, thanks for watching this. I hope you learned lots.